Welcome aboard to CS50 and computer science itself. So what is computer science? Well, put simply, it's the study of information. Like, how do you represent it and how do you process it? But more fundamentally, what we'll teach in this class is computational thinking. That is to say, the application of ideas from computer science to problems of interest to us within the class and problems of interest to you after the class. And so at the end of the day, what computer science really is about problem solving, ergo that sort of global applicability. And by problem solving, we mean something quite simple. In fact, we can distill it as follows with this mental image. This is problem solving. You've got some problem to solve, thus known as the input that you want to solve. And the goal, of course, to problem solving is to actually produce a solution. So the output in this model would be the solution. The interesting part ultimately is going to be in how you process that input and turn it into that output, ergo solving problems. But before we can do that, we all kind of have to agree how to represent these inputs and outputs, especially if we want to do it in a standardized global way using literally computers, be them laptops, desktops, phones, or most any other kind of electronic device nowadays. So how can we do that? Well, there's different ways to represent information in the world. For instance, if I were to take attendance old school style, maybe in a smaller room, I might do 1, 2, 3, 4, 5, 6, 7, and so forth, and just count people on my human hands. That's actually known as unary notation, otherwise mathematically known as base 1, because you're using your fingers literally in this model as digits. But a little quick question, how high can you count with one human hand? 5 is incorrect if you use a different base system than 1. So it's obviously correct if you're just using unary and just counting 1, 2, 3, 4, 5. But I dare say I can come up with more patterns in my human hand alone that would enable me, without a second hand or a couple of feet, to count higher than 5. In fact, maybe for those more comfortable, how high could you actually count on a single human hand, perhaps? So 31, believe it or not, is in fact the correct answer. But why? Well, here I initially started pretty naively, 1, 2, 3, 4, 5. And I just kind of combined all of my fingers and counted the collective total. But what if I'm a little more clever and take into account the pattern of fingers that go up? So maybe this is still 0. This is 1. But now maybe we just agree universally that this is 2, even though it's just my single pointer finger. Maybe we all just agree that this is 3 with 2 fingers up. Maybe we agree that this is often offensive with just 1 middle finger up. But this would then be 4. This could then be 5. This could then be 6. This could be 7. And if I keep permuting my fingers in this way, allow me to spoil it, this would be, in fact, 31. But again, why? But the difference here is that we're no longer using unary, or base 1, as a mathematician would say, but rather base 2. Because if we take into account not just the total number of fingers that I'm using, but whether each finger is down or up, being therefore in 2 potential states, down, up, A, B, black, white, however you want to distinguish those 2 states of the world, you're now operating what's called base 2. And perhaps more familiarly, even if you're not a computer person per se, this is the so-called binary system. And odds are, even if you're not a computer science person at all, you probably generally know that computers only understand or speak what alphabet, so to speak. So ones and zeros, zeros and ones, otherwise known as the binary system. And in fact, there's a term of art here that's worth noting. When you're using zeros and ones, which of course are a total of 2 digits, you have binary digits, so to speak, bi implying 2, which means there's 2 possibilities, 0 or 1. If we actually get rid of some of these letters and then join these 2 phrases, here you have a technical term that is a bit. A bit is just a binary digit, which is to say it's a 0 or 1. And this is in contrast, of course, with the system you and I know as the decimal system, dec implying 10, because in the real world, you and I daily use 0 through 9, which is 10 possibilities. Computers only use 0 and 1. That is to say 2 bits to represent information instead. So how do we represent this information, especially when at the end of the day what we're using are indeed computers and electronic devices? Well, if I want to represent 0, I can actually think of this as kind of analogous to the physical world. Maybe I have a light bulb that's off or on, controlled by a switch that turns it off or on. So you can think of a binary digit that is a 0 as really just being a light bulb that is off. By contrast, if you think of a 1 in the digital world, as of course being the second of two possibilities, you can think of that in the human or analog world, the physical world, as being a light bulb that is on. And in fact, what's inside of your Mac, your PC, your Android phone, your iPhone are millions of tiny little light switches known as transistors that just can be turned on or off. And essentially, you can use those transistors to store information, because if you want to store a 0, you turn one of those switches off. If you want to store a 1, you turn one of those switches on. Of course, that sort of invites the question, well, how do we count higher than 0 or 1? Well, we would seem to need to use more than just maybe a single bit, a single light bulb. So if we wanted to count higher than, for instance, 0 or 1, why don't we go ahead and maybe do this? So just so I have some place to put these, let me borrow some of our actual physical light bulbs here from the stage. And let me propose that now, with 3 bits on the stage, 3 light switches, 3 transistors, whatever metaphor you're most comfortable with, this is how a computer would represent a 0, because all of them are off. So it's off, off, off. But if a computer wanted to count to 1, we could do, naively, this. We could turn this on. And if a computer wanted to represent 2, we could do this. And if a computer wanted to represent 3, we could do this. But I'm kind of painting myself into a corner and not using these light bulbs as cleverly as I could, because at the moment I've only counted as high as 3. So if I want to count to 4, to 5, to 6, I'm going to need more and more light bulbs. Can we be a little more clever? Well, again, someone else who's among those more comfortable, what's the spoiler here? How high, using binary 0s and 1s, could I count with 3 light bulbs total? And back? Yeah. So 7 here is the answer. And if that too, you're sort of wondering, how are people figuring out 31 and 7? That's the goal at hand here. So let me do this. Let me turn all of these off again so that my 3 light bulbs or switches, again, represent 0. And the first one's easy. This is how a computer would represent the number 1. It would be on, off, off. How, though, is a computer going to represent 2? Well, just like my proposed finger example, let's do this. Let's turn this one off and this one on. That is how a computer would represent 2, by saying off, on, off. In other words, 0, 1, 0 would be the way to pronounce it digitally. What if I instead want to represent 3? That's how on my finger I did this with 2 fingers. Well, I'm going to turn this one on. This is 3. Now this will, for those less comfortable, be non-obvious. This now is how I would represent the number 4. This is how I would represent 5. This is how I would represent 6. And this, as per the spoiler, is how I would represent 7. So perhaps very non-obvious what it was I just did or why I chose those patterns. But I dare say if you sort of rewind in your mind's eye, or literally later on video, you'll find that I actually did show you 8 distinct patterns of light bulbs. The first one was off, off, off. The last one was on, on. And there were another 6 total in between then. Well, wait, why 7? Well, if you start counting at 0, and I claim there's 8 possibilities, you can only count from 0 to 7, as we will soon see. So how are these patterns coming about, and what is it that our computers are actually doing? Well, it's actually doing something a little like this, quite like in decimal. So in the human world, you and I are very much in the habit of using base 10, 0 through 9, aka decimal. Well, how do we use it instinctively as humans? Well, what's this number obviously on the screen? 123. But why is it 123? Like, for years, you haven't really thought about why this pattern of symbols or digits on the screen, 1, 2, 3, represents mathematically this number that you know, obviously, as 123. But if you rewind to grade school, odds are, like me, you were taught that the rightmost digit is in the ones column. This second digit is in the tens column. This digit is in the hundreds column, and so forth. So even though none of us have to do this math explicitly, what you're instantly doing is 100 times 1 plus 10 times 2 plus 1 times 3, which gives you 100 plus 20 plus 3. Oh, that's why it is 123, because these digits in this order have that significance. The digits to the left have more weight, so to speak, than the digits to the right. So what can we take away from this? Well, let's generalize it first as just any 3-digit number. So number, 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 the ones column, the tens column, the hundreds column. But there's some math going on there, and it's not particularly sophisticated. Those are actually powers of 10. So 10 to the 0, 10 to the 1, 10 to the 2. And there's your decimal system. Because the base in this value is a 10, that's because there's 10 possibilities for each of those placeholders, 0 through 9. But in the binary world, in the world of computers, where all they have are zeros and ones, why? Because all they have physically is transistors, tiny, tiny, tiny light bulbs that can be off or on. If you only have 2 digits to play with, the 10 base should, of course, become a 2 base. And now if we do some math here, 2 to the 0, 2 to the 1, and 2 to the 2, you get the 1s column, the 2s column, the 4s column. And if we keep going, 8, 16, 32, 64, 128, and so forth, it's powers of 2 instead of powers of 10. But this is to say computers represent information in exactly the same way you and I have since childhood, but they have fewer digits at their disposal. So these columns need to be weighted differently. So we can still count from 0 all the way up toward infinity. So what does this mean? Well, here we have 3 bits on the screen, 0, 0, 0. If we were to convert this now mentally or on paper pencil to decimal, how do we do it? Well, 4 times 0 plus 2 times 0 plus 1 times 0, that gives us the mathematical number you and I know as 0. That was 3 light bulbs, off, off, off. Well, what if we turn on 1 light bulb all the way on the right? What decimal number does this binary number, 0, 0, 1, represent? Just 1, because it's 4 times 0, 2 times 0, 1 times 1. Here's where things got more interesting, even if non-obvious in light bulb form or even physical hand form. 0, 1, 0 in binary is what in decimal? 2, because it's 2 times 1, and that's it. 0, 1, 1 in binary is, of course, now 3. This is now 4. This is now 5. This is now 6. And 7, on, or 1, 1, 1, is the highest we can count with these 3 bits. All right, so how might a computer intuitively count as high as 8? What do you need to do, presumably? You're going to need to add a bit. So you need another light bulb, another switch. You need more memory, so to speak, to use nomenclature with which you're probably familiar. So in fact, if we change all of those to 0, but we give ourselves 1 more bit for a total of 4, that's got to be the 8's place, because it's just another power of 2. So 1, 0, 0, 0 is the decimal number 8. You don't say 1,000 in binary. You literally say 1, 0, 0, 0. But that is the number you and I know as 8. And you can keep going up and up and up. And how then computers with Excel or any kind of number crunching software count really high and keep track of really big numbers? The computer just throws more and more transistors at it, more and more bits to count higher and higher and higher than this. Turns out, though, 1 bit, 3 bits, even 4 bits aren't that useful in practice, because like literally you can count as high as 7 or maybe 15 or 31. So more commonly, as is commonly known, is to use a byte of bits instead. How many bits is in a byte for those familiar? So it's just 8. Why 8? It's just more useful than 1 or 2 or 3 or some other number. And as an aside, it happens to be a power of 2, which is just useful electronically as well. So a byte then is just 8 bits. And here are those columns I rattled off the top of my head. Here is how a computer would represent 0 in decimal, but using 8 binary digits or bits. Little trivia, and again, this is not what computer science is about, but it helps to sort of know sort of the lower bounds and the upper bounds of these kinds of values. How high can you count with 8 bits or 1 byte? If this is 0? Yeah, so it's actually 255. So if I were to change all of these zeros to 1s and then do some quick mental or calculator math, 128 plus 64 plus 32, 16, 8, 4, 2, and 1 would actually give me 255 total, plus 0, which gives me 256 total possibilities. So this is only to say, this is not, again, the kind of math we'll frequently do, but you'll commonly see in the computer world and programming world powers of 2, numbers like 255, 256. Why? Because these are the common units of measures that systems tend to use. So let me pause here and see, with respect to binary, zeros, ones, transistors, and the like, any questions or confusion we can clear up? A really good question. Why are bits just on or off instead of maybe sort of 0%, 50%, 100% by playing with voltages? So the voltage inference of yours is actually correct. That's what computers typically do. Maybe they use 0-ish volts to represent 0, maybe 5-ish volts to represent represent 1. It turns out it's just really easy to do extremes in computers. If you start to split that range of voltage levels, for those who remember any of their electricity, it just gets harder and harder to be exact. And if you get things a little too murky, you might mistake a 0 for a 1 or a 2 or a 3. So it turns out it's just simpler to use the binary system. But there do exist computers known as ternary computers that actually use 3 values, 0, 1, and 2, which is somewhere, of course, between binary and decimal. But you can do different things. It's just simple on and off. And case in point, I don't want to really be dramatic and turn off my computer, but if I pulled out the power plug, that could be off, literally, aka 0. Plug it back in, that's a 1. There's just a cleanliness and simplicity to that. Other questions?